Alright, so now the next one that we want to do is problem 53. A uniform thin rod of length that's 0.5 meters and mass that's 4 kilograms can rotate in a horizontal plane about a vertical axis through its center. The rod is at rest when a 3-gram bullet traveling in the rotation plane is fired into one end of the rod. As viewed from above, so this is a top view, the bullet's path makes angle that's 60 degrees with the rod. If the bullet lodges in the rod and the angular velocity of the rod is 10 radians per second, immediately after, so it's going to rotate like that. Immediately after the collision, what is the bullet's speed just before the impact? So you also find the velocity right here. Okay, so let's look at this diagram. So this is the rotation axis. So this bar can rotate freely. Now initially this is not moving. All right, so there's the initial angular velocity, of course, is 0, and which means that the whole thing is not moving. Now let's do it this way. So now you have 5 bullets in that direction. So that bullet is going to encounter this thin bar, and then it's going to collide with this thin bar. And after collision, we found that the bullet is lodged at that end, at the end of this rod, and the whole thing starts to spin at the rate that's at the 10 radians per second. So you can just look at this picture as again, this is this involves linear motion and also rotation, and this is the motion that's that is applied in reference to this this reference point. There is a distance, so there is the angular momentum. When this moves, there's a linear momentum, and when this in reference to this point, it has an angular momentum. So the whole thing, the angular momentum should be conserved, for isolated system. So you should set up equation like that. So your Li is equal to Lf. So the question is, what goes into Li and what goes into Lf? So before collision, this bullet is traveling in that direction. So we know that the expression for the angular momentum will be R cross F. So your Li is equal to R cross P. R cross P. So you have the radius, the distance, and then times the mass, and then times the velocity, and then times the angle between them. Okay. So what is the the angle between them, between the velocity and the radius? So what is the radius? This is your reference point. So the radius, of course, is this. Is the hull of the bar. So this is your radius, and this is the velocity. So the angle between them here is 60 degrees. So we can utilize this expression to calculate the magnitude of R cross F. So you have your R. Your R, of course, is your R here. This is hull of the L. So it's 0.25. The mass of the bullet. So that's the mass of the bullet, which is 3 grams. How many is a gram? Velocity we don't know, and then sine of the angle between them. The angle between the R and V is 60. Okay, so this is the initial angular momentum. What about your final angular momentum? Your final angular momentum, the whole thing is going to move, and then at this rate, that's 10 radians per second. So the angular momentum would just be equal to rotation inertia of the system times the angular velocity. So the question is, what is our I? We know that this is a thin bar, so it has, it's rotating about the center, center mass. So there is a rotation inertia regarding this thin bar. In addition to that, after collision, the bullet is going to, lodge at this point. So this additional mass can also produce rotation inertia as well. So your I should have 2 turns. One's coming from the bar or the rod, and the other one is coming from the bullet, and then times your omega. Okay, so that's basically how. And then these two quantities have to be equal to each other. So after you do that, so you'll find that then we can find our velocity. So let's first of all find out the rotation inertia of the system. So your I is equal to the rotation inertia of the rod plus rotation inertia of the bullet. So what is the rotation inertia of the rod? That would be just 1/12 mass of the rod, and then the total length of the rod. So that's 1/2 capital M and then L squared. And then what about the rotation inertia of the bullet? The rotational inertia of the bullet, that will be just mass of the bullet and then times the distance between the rotation axis and where it is located, which is just half the length. Okay, so that you have that. So that's plug in the number. So you have 112 times 4. 112 times 4. And then times your L, which is 0.5, square it. And then your mass of the bullet, which is 3 times 10 to the negative third. And then times the 0.25, you square it. So you can see that the presence of the bullet actually does contribute to the rotation inertia, although it's kind of small, but it is, there's still, some numbers there. So after you punch into a calculator, you should get a value that's 0.0835 kilograms meters. So that's the rotation inertia of the system, okay? Once you have that, we calculate this, so you can set this equal to each other. So on the left-hand side, you have 0.25 times the mass of the bullet times velocity times sine of 60, that is equal to the rotation inertia of the system, which is 0.0835, and then times the angular velocity, which is 10. So after you plug in a number, you can find that. The velocity, how fast is the bullet traveling? It's traveling at this velocity. So it's 1,285 meters per second. Okay? So this is a classic example, when you have an object that's moving, making a linear motion, but in reference, but at an angle, at a distance from the rotation axis, and after collision, it's moving. The whole thing is rotating. So you can actually utilize the expression. This is one expression for angular velocity, which is r cross p. The other expression for the angular velocity is r omega. You can see that they have to be equal to each other before the collision and after the collision. Okay. All right. And the last problem we want to do from chapter 11 is 87. So I'm going to erase this. Okay, 87. If Earth's polar ice caps fully melted and water returned to the oceans will be deeper by about 30 meters. What effect would this have on Earth's rotation? Make an estimate of the resulting change in the length of the day. So in other words, this is the Earth with the radius r. And because it's rotating, so we know it's a rotating object, and it has a mass. Let's call that mass m. It has radius r, so you can calculate the rotation inertia of this of Earth. And then when all the ice melted, the ocean is deeper by 30 meters. What does that mean? It means that the radius of the Earth would now be 30 meters larger. Okay, so this is the Earth. Your r prime now is the radius of the Earth, and then plus 30 meters. So you ask to find, and the mass is still, mass does not change because there's no adding mass to to Earth. So you're asked to find you're asked to estimate what kind of effect it will have on Earth. Okay, so how do we approach this problem? Again, this is an isolated system. When you have an isolated system, it means that, and then this is rotating. Let's say this is rotational axis, so it's rotating like that. So when you have an object that's an isolated system and is rotating, angular momentum has to be conserved. In this case, you can calculate the angular momentum, and then and the angular momentum of this picture should be equal to the angular momentum of this picture. Doesn't really matter whether the radius changes or not, because it's an isolated system. Okay. So how do we calculate? How do we estimate? So we know that Li has to be equal to LF. How do we calculate LI? And how do we calculate LF? If it's rotating, it has rotation inertia, that's called the I. And after the ice melted, you have your I prime, okay? And let's say initially it's rotating at omega, now it's rotating at omega prime. So this is how you set up the equation, before and after, okay? So we know that the I, rotation inertia, will change because the radius changes, so I has to change. So that's set up equations like this. And omega, what is omega? Omega basically is in relation to the period. Omega is simply equal to 2 pi over t. So now we know the mass of the Earth, we know the radius of the Earth, we also know the period of the Earth after you rotate a day. So you can calculate, we have all the information in front of us, so we can actually see what kind of effect it will have on the period. So your omega prime here will be equal to 2 pi over t prime. Okay? So what is the rotation inertia? The rotation inertia of a solid Earth, that's just right here. The expression is 2/5 mass of the object and then radius squared. So your I here, you have, so your I here will have 2/5 mass of the Earth and then the original radius of the Earth, and then times your omega is 2 pi over t, okay? And that has to be equal to the new rotation inertia, which is 2/5 mass does not change, but now it's r prime squared, and then you have 2 pi over t prime. Okay, so now we can actually remove this 2 pi get cancelled. So what we have here is that you have your r squared over t, that's equal to r prime squared over t prime. Okay, so now what we can do is that we can rearrange this, so you have your t prime, the new period over the original period, that's equal to r prime squared over your r squared. Okay, so what is our r prime? Our r prime is r plus 30 squared, and you have your r squared. So what we're going to do is that we're going to move this r inside, put it in this parenthesis. So you have 1 plus 30 over r, and then you square it. Now when you have something like this, 30 over your r is a very large number. So you can do estimation. So this becomes, so your t prime over t now becomes 1 plus 2 times 30 over r. This is what we call the Taylor expansion, when you have 1 plus x, and then when x is so small that when you have square root, that's just 1 plus 2x. Okay. So now we have this. So what does that mean? That means that you can calculate this. So you have 1 and then plus 60 over your r. And what is the r value? Your r value is the radius of the Earth is 6.37 times 10 to the 6. Okay, and you can see that. That's why we can do the estimation, the approximation, because it's so small. Okay, so after you do the calculation, you will have 1 plus 9.4 times 10 to the negative 6, and that's the ratio. So in other words, your t prime, the new period, is equal to this times the period of the Earth. Okay, so we can calculate, and then we know that what is our t? Our t is for a day. 1 day that gives you this amount of seconds. So you can calculate, plug into that equation, you can calculate your t prime. And your t prime, after you do the calculation, that will be 86400. So you can see that you still have the same numerical value before the decimal point. After the decimal point, that's 812 seconds. So what is the effect of that you have on Earth if all the ice on the polar cap melted? This is the effect. The period is actually longer by 0.812 seconds. So we gained this extra time for a day. Okay. So the delta t, after you do the subtraction, you get 0.812 seconds. Okay, so the effect is kind of small, but it is there is an effect, nevertheless. Okay, so that's basically we gain extra time for a day. That's basically what this means. And it just says that when there's a composition within this this distribution of the Earth's changes, it will have an effect on the length of the day because your eye is different. And in order to keep this constant, then the rotational rate, how fast it rotates, has to be changed as well in response to the requirement for angle momentum conservation. Okay.